Thank you, and thank you for inviting me here. This beautiful campus, my first time at ICTS. I'm going to talk about this recent work we did about lattice operators of quantum loop algebras, and I've taken the liberty of already writing main theorem of this work. So I'll just read it for people sitting over there who probably can't see. The result is about rationality of certain series, which we've been calling Chari-Presley series because it arose in the first works of Chari and Presley on classification of irreducible representations. So if you take one of these series and you evaluate on a finite dimensional representation, they become rational functions. So that's the first result. Then we'll see that you can take their normalized limits near 0 or infinity. And once you do that, you recover the action of a co-root lattice on such a representation. So many of these characters we have seen last week in Professor Hernandez's lectures. We also saw it in the first talk. These series were denoted by capital lambda sub IU in the last lecture. And these lattice operators were denoted by T sub omega I. But I will probably introduce all of this anyway. And for simplicity, I'm going to assume in this talk, G will be SL2. So I'll denote the quantum loop algebra of this as UQ of L SL2. If you let Q go to 1, you recover enveloping algebra of the Lie algebra. Of Laurent polynomials in one variable coefficient from SL2. And if you further just evaluate T to, let's say, 1, you just recover USL2. So these are the three parts of my talk. I'm going to start from USL2. I'm going to tell you what these series look like and what the theorem looks like. Unfortunately, in that case, there is no co-root lattice. So we're not going to see the illustration of the second part of the theorem, which will become clear once we move to the loop and then to quantum loop. And if I have time at the end, I will tell you why we were doing this. The motivation will come at the end, hopefully. Otherwise, you can ask me later. So, okay, first part, USL2. I know it's not necessary, but here it is. In this case, the series that I'm talking about, I'll just denote by little p plus or minus z. Looks like this. It's exponential of a logarithmic type sum. Actually, it is a log. And as such, it lives in our algebra with power series in Z inverse or Z, depending on the superscript plus or minus. This is actually just log, so I shouldn't be too much around the bush. So this is exponential of h times log 1 minus z to the minus plus 1, which I can further write as 1 minus z negative plus 1 raised to the power h. And now I think it's obvious that the theorem is true. From the SL2 representation theory, you know that on a finite dimensional representation, H always acts as diagonalizable matrix with integer eigenvalues. So if H is an integer, this is a rational function of Z. But I still want to give you another proof, because this one doesn't generalize. As we move up in the layer, the categories of finite dimensional representation stop being semi-simple. So even if you have classified irreducibles, which people have, you can't reduce to that. So a different proof of this. So this is based on just some algebra. So first you prove this identity. So it's a PBW straightening formula, and here I'm using divided power notation. So x to the round parenthesis n will always mean x to the n divided by n factorial. And this you can do it by induction on smaller of m and n, use these relations. Then you can use this to put it in a generating series. You can say sum -1 to the n, e to the n, f to the n, z to the minus n is exactly p plus z, L from 0 to infinity, -1 to the L, f to the L, e to the L, z to the minus L. Here I'll be using the different form of p plus because I've already written it like this. So you can use Newton's formula to write it. So this will become I hope this binomial notation is also clear for a variable. It's just a polynomial in that variable of degree L, given like this. All right, so I hope now it's clear that the p plus is rational. If you're in a finite dimensional representation, f's and e's act nilpotently. Both this infinite sum become finite, so p plus is rational. Once we go to further, these are used to classify irreducible representations. So we heard about Drinfeld polynomials last week. Drinfeld polynomials are Chari-Presley series evaluated on highest weight vector. You see, how am I doing on time? That's good. Other questions? So what about this normalized limit, which is also clear? I can't send p plus, I can't start z is equal to 0. But if I multiply by z to the h, I can. So that will become normalized limit. So maybe I'll write it here. Save some board space. And like I said, in this story, SL2, there is no co-root lattice, so I can't illustrate the next part of the theorem. All right, that's the first part. And I shouldn't have used that, huh? All right. Now we move to the second object. The algebra of Laurent polynomials in one variable, coefficient from SL2, we saw it in last talk. And this is, again, easy to write down in generators and relations. Which was we also saw in last talk. There is no central extension, there is no derivation. You just take the bracket as you will do in SL2 and increase the subscript. So what happens to Chari-Presley series in this case? I'll denote them a capital P. All look exactly the same, except this h becomes plus or minus n. You can see that if you're evaluating at 1, it just means erase that subscript. All these h k's go to h, all the e k's go to e, all the f k's go to f. Then you recover the previous one. Again, we know where it lives. It's in our algebra. If you want to just see an example of why it becomes rational, which is the theorem, we can maybe have a small example of a representation called evaluation representations, which we also saw in last week's Professor Ananda's lectures. I can take algebra set T is equal to alpha, where alpha is some non-zero complex number. I go to USL2. I can take two-dimensional representation, let's say. Let me write down formula. Let me just fix it. The basis of weight basis V plus and V minus. Then I can evaluate, for example, one of them on, let's say, V plus. So all these HNs will turn into alpha to the N, and we'll be back to, Amrit, is the question? Yeah, I keep changing the notation. So on V plus, this will become exponential of, again, negative sum. And all these HNs will turn into alpha to the N. And again, it's the expansion of log, so I'll just get this. This is, in fact, a polynomial in Z inverse. And this was a theorem that was proved by Chari in 1986, that if you take this thing and you evaluate on the highest weight vector, in this strong sense that all the E's have to act as zero, then it will always become a polynomial. Now I'm saying that if you drop the first condition about being the highest weight vector in this very strong sense, you still maintain rationality. So proof, it's going to take a little bit of time. But it's exactly what I did for SL2. So first you need a straightening identity. So analog of star, I'm not going to write. You straighten E0 and F1. And it was obtained by Garland in 1980, this paper called Arithmetic of Loop Groups. So you can look at the paper and find this identity. I will write the second one though. So this one becomes the negative L. I'm still using the divided power notation. And here the only thing I have to explain is what is this E plus? These are what called half currents. So you only encode all the E's with the non-negative subscript into a generating series. If you read the Garland paper with some tenacity, you can get this second one out of it, which is also Chari's argument from 1986 was also based on this identity from Garland's paper. And she proves that the left-hand side is equal to just P plus modulo left ideal generated by E pluses, EKs. So that's what was based here. So if you imagine you're on a vector where all the E's are going to act as zero, this sum just goes away, it's just one. So you recover P plus as a polynomial because these F's have to stop at some point. So now we need a little bit more. We need a rationality result, so I'll write it as a separate proposition on a finite dimensional representation. E plus Z and E minus Z. remainder of the generators, they are actually the same rational function. So these are, to write it precisely, are Taylor series expansions. One near infinity and the other one near 0 of the same rational function. You want to convince yourself on this tiny little example, you can work out E plus Z acting on V plus in my running example of C2 evaluated at alpha. This will just become Z over Z minus alpha. Sorry, the lowest weight vector, then it becomes the highest weight vector, which is also same as E minus. This always holds. The same statement after you take this series and you take its commutator with F1 will give you H plus Z. I want to write equal to, but that's a sin. And H minus Z. I'm just going to write same statement. It's the same rational function. You expanded near infinity or expanded near 0. You got those two series. So now the rationality of P plus follows on a finite dimensional representation. Both these infinite sums become finite. And this thing, which was already an infinite sum, so could have caused us some problem, is actually a rational function. So both sides are rational function. P plus is a rational function. Corollary 1. I might forget at some point to say once evaluated on finite dimensional representation, but just remember that's going to happen anyway. The second thing that follows, I only actually proved it for P plus, but there is an automorphism of this algebra. Flip T to T inverse. You can use that to get P minus. And the second thing is they're related, so that normalized limit exists. So corollary 1, corollary 2.
Sachin,
Yes.
so the rational function will change depending upon the vector that you act upon.
Right. So you can imagine this end V valued rational function. Right. So I take the algebra and I map it to end V via the representation map. And it becomes all the entries will be rational functions. Maybe I will show you a proof of this because it's kind of fun. The way they defined it are in terms of exponential of a series. So you can take the logarithmic derivative. Right? So I can take derivative with respect to Z of log of P plus. So erase that exponential sign from right-hand side and take derivative with respect to Z, and you will get H minus N, sorry, H sub N, Z to the minus N minus 1, and going from 1 to infinity. This is almost H plus, but not quite. And similarly, if you do it for P minus, get a minus sign here, and then I have H negative N, Z to the N minus 1, which is Z inverse of H minus Z. But remember from the second part of this proposition, they are same. These two are the same. So what I get is Z inverse H0 plus logarithmic derivative of P plus is logarithmic derivative of P minus. Well, then you integrate it, so you get H0 log Z plus P log of P plus is equal to log of P minus up to constant of integration. And then you exponentiate it, and you get Z to the H 0 P plus is equal to exponential of that matrix K times P minus. Again, I will say it, all this action is happening inside endomorphisms of V, and in particular, in the commutative subalgebra of endomorphism of V generated by all these H's. So I don't have to worry about where am I putting these exponential, all these things commute. And as Z goes to 0, this goes to 1. So let's see. So I guess I have explained in the non-quantum case, what are the series, how do you prove rationality, what is the normalized limit. I still have to tell you what is the co-root lattice. So that will take a few minutes. Any questions meanwhile, while I'm erasing the board? So to get the action of this co-root lattice, you have to study the action of the Weil group. And for that, you have to work with the other presentation, the one that Denise mentioned first, the Kac-Moody presentation. So I'll just draw the basis of this Lie algebra, and I'll tell you what this Gauer-Katz isomorphism is, which I'm sure you know, but doesn't hurt. I have E0. Is the green color visible on the green board? Probably not. It's okay. So this is the basis of our loop algebra. And we have one SL2 triple sitting in degree 0. And then you have another SL2 triple. Fine. Like this. And these are enough to generate the entire algebra. If you have F1, I can use this E0 to get the rest. Once I have these, I can use H1, F1 to get this, and you keep going. And similarly, you do the same thing. So the result of Gauer-Katz that this Lie algebra, this enveloping algebra I just presented is isomorphic to the enveloping algebra of the Lie algebra associated to a fine Dynkin diagram, in this case, of type A11. So it corresponds to Dynkin diagram of node 0, node 1. So this one has generators E1, H1, F1, E0, H0, F0, and you write down the same Chevalier representation, but with this Cartan matrix in mind. And I'm working with loops, so I have to kill the center, so H0 plus H1 has to be 0. Yeah, yes. I don't know, I always thought it was Gauer-Katz isomorphism. Is it just Katz? Because you can correct me and I will change it. Yeah, this is also, yeah, this is Kac-Moody algebra, but without central element and the derivation. And this corresponds to, this is node 1, the SL2 triple E0, H0. and F0. And this other one we got here, the role of E will be played by F1. The role of H will be played by minus H0. The role of F will be played by E minus 1. So that's an isomorphism. Yes. Is there? Probably. Sorry? This one? The bracket of xk with yl is xy sub k plus l, where x and y are h, e, or f. Yeah. Yeah. For example, hk with hl is 0. Ek with el is 0. Something else? The advantage of this is there's a way to make while group show up here, and there's a way to make it act on finite dimensional representations. In this case, the while group is generated by two elements, S0, S1. Their square is 1, but there is no other relation. So this is an infinite dihedral group. And just like we do with dihedral group, you take product of two reflections, you get a rotation. You can give a different presentation of this, where little s is little s1 and little l is s0, s1, s0 times s1. For finite dihedral group, product of two reflections becomes rotation of some finite order. Here it has infinite order. That's the difference. The way you make it act, well, while group doesn't act. It's a subquotient of your Lie group, so we have to like take its extension. And this formula was given by, I think, Jacques Tietz. There are three exponentials, and I'm running out of room. If so, this will act. You don't need finite dimensional. You just need to know that E's and F act locally nilpotently to make sense of this. And that's how lattice operators act on finite dimensional representation. In this case, there is only one lattice operator because the co-root lattice is rank 1. This little L guy. You take S0 tilde, S1 tilde. That's how you get the action on the finite dimensional representation. Now at least I can write the second part of the theorem somewhere. Maybe I can erase this proof. It's still good. At this normalized limit, C, is actually this lattice operator inverse, and you have to correct for a sign. So this is what I mean by this. The normalized limit recovers the action of co-root lattice. L tilde would be with the S0 tilde, S1 tilde, yes. Again, you can work this tiny example if you like. We already computed what P plus Z is. Normalized limit would be multiplied by Z and set Z is equal to 0. So C will become negative alpha. And so lattice element will become alpha inverse. This is really too low, I'm assuming. And this example is tiny. You can actually work out this product of three exponentials. For example, for SL2, you take the product, it just becomes this matrix. Then you put an alpha for the other one, multiply two by two matrices, and that's what you will get for its 1-1 entry. Okay, questions, comments? So now we move on to level 3, and I have 20 minutes, and I'm gonna do a terrible thing. I'm just gonna throw in cues everywhere. Yes? Yeah, the isom, yes. Yes, this is isomorphism of Lie algebras, hence I'm just writing it everything for an enveloping algebra because I'm going to start throwing Qs everywhere. If you have a symmetrizable Kac-Moody algebra, you can write this formula for each node, and you get the action of the corresponding braid group, well, extension of while group. Once I throw in Q, it's going to be actually braid group. They're not going to square to 1 anymore. Yes, if you want extended affine, this will give you a affine braid group or a affine while group. Then you can throw in diagram automorphisms by hand, and you realize that extended affine is diagram automorphisms, semi-direct product affine. It won't act on representations though. It will only act on the algebra.
So you have Garland identities and other types?
Sorry?
SL2 wrote it very explicitly, Garland identities.
Yeah, so this is on each node you have a copy of SL2. So you just put i's everywhere and the Garland's formula works. Yeah. No? No, this is the loop generators. Yeah, this is a loop presentation. For this presentation, sorry, I made this. For the other presentation, I'm using capital letters as Dennis did. Just lucky that our notations lined up. We didn't synchronize this. Okay. Level 3. Oh, I could have erased this too. Maybe I use a red color or something, so it'll be more visible. These generators, but relations look more complicated. This is called Drinfeld's loop or new presentation. These were given by Drinfeld in 1988. I will only write maybe 2 of them, which are useful. HK is still commute. And the commutator of H with E or F, you can write down. So this is a Q setting, so I should write Q is a non-zero complex number, not a root of unity. And I'm going to be using, instead of numbers, Q numbers, which go to n as Q goes to 1. And similarly, my divided power notation is going to change. So in the denominator, you will have a factorial. All right. There are more relations, by the way. I'm not going to write them. So now it's for Chari-Presley series. Okay, I'll change it a little. Here you get Q to the plus or minus n, and this n becomes quantum. So far, so good. We can forget about the example for now. The time is already drawing near. And in this case, the result I'm just erasing is due to Chari and Presley from 1991. Which says that if you take sum, -1 to the n, q to the n square, that's probably fine here, k to the negative n, t0 to the n, f1 to the n, z to the minus n. All right, great. This is congruent to p plus z mod left ideal generated by all these t's. Professor Hernandez mentioned Drinfeld polynomials a bunch of times last week, but he never defined them. So here is a definition. Once you evaluate this thing on a highest weight vector, this will become a polynomial in Z inverse, and that's the Drinfeld polynomial. So analog of this came much later also in the works of Chari and Presley. In 1997, their paper called Quantum Affine Algebras at Roots of Unity. I'm not going to write it again because I didn't write it for loop algebra either, but I will write this one. I could have kept it, by the way. It looks a bit more complicated, but if Q goes to 1, I didn't write what K is. K is Q to the H0. So K goes to 1, this disappears, Q disappears, and you will recover the identity I just erased. All these terms will become the same and will come out, but now they won't, they were kind of stuck in the middle. All right. E plus is still the same. We have a same, ouch, rationality property. So I put Q there, but I'm forgetting it everywhere. I'm sorry for that, but now we're in the Q setting. So this part is still the same. On a finite dimensional representation, E plus and E minus become the same rational function. The second part changes a little. There's a different set of generators people use. So I will write that. So K times, I'll just write once. Become the same rational function, same statement. And these are usually denoted by psi plus or minus. The 1 is not obvious yet because there is a P at a shifted point. I first have to tell you what equation these P plus or minus satisfy. This is no longer a differential equation, it becomes a Q difference equation. Let me just write 1. So it's a Q difference equation. That means if I scale Z by Q square, it's the same as the value of your function at Z times something. This is just a little scale. So this goes to 1 as Z goes to infinity for plus, and as Z goes to 0 for minus. This is just this K in the front, which changes the values. So now we can see that if I take this P out of here, and put it here, this ratio becomes a bunch of products of psi, which are rational. So everything, once you evaluate on a finite dimensional representation, this becomes a finite sum, this becomes a finite sum. Everything here is rational. Hence, first corollary. The second one is also pretty neat, except now I don't have to work with the differential equations. I have to work with difference equations. So this becomes a fun little fact from complex analysis. So here I have Z to the H0, P plus Z, and P minus Z solve the same difference equation. That means the ratio has to be Q square periodic, and they're rational. They can't have any poles. They're holomorphic. They become holomorphic function on elliptic curve. Have to be constant. It's also easy to see there, well, it's relatively easy to see there, this constant will be invertible, the inverse here. Because these are rational functions which are identity at a specific point in your Riemann surface, infinity for this, 0 for this. So generically, they will always be invertible. They only have finite set of poles or finite set of zeros of the determinant. So just pick a point where they're both non-vanishing, if they're both invertible. Evaluate there, that's your constant C. And the theorem I raised is still true. Maybe I can write it over there. Well, except now I have to tell you that there is a version of this with Q's everywhere. Due to back. And Professor Hernandez told me last week I should put Damiani's name because she's the one who gave the complete proof. So this will be the Drinfeld-Jimbo style quantum group. Hey, I may have time for motivation. That's nice. And this map changes a little. You have to put K here and K inverse here. Wild group is no longer a wild group, it's a braid group. Yeah, I'll just. And there are no relations. Free group on 2 letters. I can still define this L with the same formula. So maybe I'll just use capital letters now, S0, S1. So this will be the lattice element. And the way this formula changes is due to Lustig. So I have to put Q's everywhere. There's one more factor, sorry. And Q exponential is defined as place n in the denominator by the quantum n. Right, but here it makes no sense because there are no braid relation. But yes, that's true. That's what Lustig proved. I know. I know. Okay, at least I can say as Q goes to 1, this guy goes to the previous one.
There's no meaning
well, there's a coproduct identity which kind of uniquely determines it then. So there is a identity again due to Lustig. Some truncated finite R matrix of quantum SL2. So you can recover R matrix from this kind of coproduct. But if you impose this and the Q goes to 1, whatever, then uniquely determines this formula. Sorry, this is SI, not Li. And let me just write the theorem. So this normalized limit that I just showed you exists. Is negative Q inverse to the H0 time this, should I put a tildes again? That's fine, okay, L tilde inverse. So earlier it was -1 to the h0, that changed to a little q, but you have the same result. Okay, so I still have a few minutes. I can answer some questions and I can tell you some motivation. But the content is over. All right. We had basically 3 motivations in mind. So I'll probably start with geometry because that's part of the conference. So the result of Nakajima that this quantum affine SL2, quantum loop SL2 acts on equivariant K theory of cotangent bundles to Grassmannian. And was a conjectural formula that was given by Kotis, Kumnitzer, and Licata in 2013, how the lattice operators will act under this Nakajima's homomorphism. And now we can just compute from our theorem. L acts as multiplication by this line bundle on K of so what is W? W is C to the n, the trivial vector bundle, but its equivariant structure is non-trivial. Let me just write it C to the n, but you base space times C to the n. And this V is the rank K tautological subbundle. And this confirms the conjecture of what is Gautam from 2013. That's one. Second motivation was we wanted to prove, okay, this is not going to make sense because I didn't define the words. Dirichlet coproduct of L is L tensor L. It was expected, but from this horrible looking 6q exponential that you see here on the board, this L is S0 times S1, almost impossible to prove. That's the second corollary of our theorem. Dirichlet coproduct of L is L tensor L. If you don't know what this is, don't mind. It's only 1.5 minutes left, so I can say whatever I want. The thing is, if you combine this Lustig's coproduct formula with that result, you can give a different proof that the trigonometric R matrix is meromorphic. This is trigonometric R, universal R matrix. It was mentioned in last talk, but these are finite dimensional representations. Which was another one of our motivations. We wanted to give a different proof. This result is known. It's due to Kashdan and Soibelman from 96, I think. But we didn't understand their proof. We wanted our own. So this one we understand. And the third motivation is even has more words. 19 seconds, you can do it. So we have a homomorphism from loop SL2, quantum loop SL2 to completion of Yangian. And we wanted to show this doesn't live here, it lives in the completion. L goes to just exponential of some element. So that's the third corollary. Yes, okay, I'm done.
Yeah, thank you very much. So I just have a quick question. So you defined this Chari-Presley series, and then what you just naively can do is act with a Lustig operator on that. And I think from your results, you can get that it acts also as a rational function, but I wonder if how the rational functions are related. So like in Chari's break group paper, you
I
can
don't
relate
know.
them.
I haven't studied the finite braid group action on this series,
I see.
but I'm expecting it will be the similar formula they have for just the eigenvalues of the psi z's. If you know the eigenvalues and you apply the Weil group element, you can tell how it changes, right?
Okay. But this is on the highest weight. You're expecting this is true for?
No, that statement is for extremal weight vectors, right?
This is for extreme weight,
Yeah.
right? But your result is for any finite dimensional
Yes.
representation.
So weights, the representation doesn't have to be reducible, doesn't have to be highest weight, but sorry. On highest weight representations, you can use their result, but you can only get the eigenvalues are rational. You don't get all the matrix entries are rational. That they say that the eigenvalues of psi have a specific form, right? You can use that form to reprove this theorem and say that the eigenvalues of this p plus or minus are also rational, but you can't get the other matrix entries. So for highest weight representations, there's a different proof which is much easier, I guess, easy-ish. But not every representation is highest weight, right? You have some counterexamples. No, we use the straightening formula. We use this identity. Yeah. I think you can take the equivariant, but then you won't get symmetry in the equivariant parameters. Oh, yeah. The way the thing goes is Nakajima's action is more geared towards Drinfeld coproduct. So it's as if you took a Drinfeld coproduct on a cotangent bundle on P1s, because you can pick a torus action on the framing vertices whose fixed point are just 1, 1, 1, 1, 1, right? For the stable envelopes, it's the other coproduct. It's the non-Drinfeld coproduct, the usual one you get on quantum groups. So there is a formula that if I take delta of L, this is L tensor L times 2 Q exponentials. I can tell you what they are exactly, but this is how it will in stable envelopes. This will be a lower triangular matrix, and you can tell if you're on the diagonal, it's just L tensor L, and further you go away, these are some Q exponentials of F tensor E's. On fixed points, it's just L tensor L. This. Yeah, on the fixed points, this. Well, thank you.